use the distributive property to simplify and do the inverse to factor. So today is a very mechanics day. So today is like a day where there's not a whole lot of real world application that we're showing today. I promise you the real world application is coming, but I feel like in order for us to understand the real world context, because we're going to have to learn a lot of the real world context, we have to have the mechanics first. And so a lot of teachers will do this a little bit differently. A lot of teachers will say, I think you need to know the real world context and then do the mechanics second. This particular time, I'm kind of feeling the other way around. So we're going to focus on some very mechanical things today, some very step process driven things without the real world application. And we're going to start with distributive property. You guys all should know the distributive property already. It's something that you learned last year. Now, obviously, I'm not going to assume that you all learned it. We're going to go over it a little bit today. So let's start with somebody who does remember the distributive property and can describe for me what the distributive property says. Jefferson.
The distributive property, I think it is when you multiply the number that's outside the parentheses and distribute it to each one that's inside the parentheses.
Okay, so Jefferson says a multiplication done outside parentheses can be distributed to each term inside. And so an example of that would be this. We have a multiplication outside a set of parentheses. And what we're saying is that we can distribute that in by multiplying to both parts. So it's the same thing as 3 times x plus 3 times 3. Now, I want you to be able to prove really quickly by doing an example why the distributive property works, or prove that it does work. So what we're going to do is we're going to look at it this way. We're thinking about this. This is 3 times this thing that's in parentheses. Well, when we think about multiplication, it's the same thing as repeated addition. So it's like saying what's in this parentheses is being added to itself how many times? 3. Okay, so let's write that down. It would be x plus 3 plus x plus 3 plus x plus 3. Well, now this is a problem that we know how to do. Right now we're actually going to use the associative property kind of to ungroup everything. So if I'm kind of using the associative property to kind of do the opposite of what we usually do. I'm just ungrouping everything. So the associative property can be used kind of both ways. It can be used to group things. It can also be used to ungroup things, since everything is addition here. Now if I want to simplify this particular problem, what am I going to do? Danilo.
You would commute your terms. So
Yeah, commute my terms. So x plus x plus x plus 3 plus 3 plus 3. Let's go ahead and simplify that. 1x plus 1x plus 1x is
3.
3 plus 3 plus 3 is Now if we come over here and look at when we use distributive property, 3 times x is 3x, and 3 times 3 is... So we can kind of see where a lot of this comes from if we start looking at it. We look at this here, this 3 plus 3 plus 3, that's the same thing as the 3 times 3. The x plus x plus x, that's the 3 times x. So we can see here kind of where this idea of distributive property comes from. And I think that you should be able to prove distributive property works. So I want to do one more example with you. And think about what this is telling me. So we're going to do this one without distributive property first. We're going to do it with the repeated addition here. So what is being repeatedly added here? What is being multiplied? What is being repeatedly added? Jalen.
Is it the one that's being multiplied?
What's being multiplied here? 2 and? The 2 and everything else. Okay? Everything else, because it's just one piece. So if I'm having this 3x plus 2 being multiplied, how many times do I need to add 3x plus 2 in this particular situation? How many times is it? How many times? 2. Okay, so this is the same thing as saying 3x plus 2 plus 3x plus 2. It's that idea that multiplication is the same thing as repeated addition. When I'm multiplying something by 2, I'm really just saying that's the same thing as adding it twice. I'm going to ungroup these. Which property am I using when I ungroup them? Associative property. If I want to continue to simplify this, what's the next step? Jesselyn? Commute. And finally, kind of use the associative property the opposite way so I can combine like terms. Now, if we use distributive property, instead of doing it the long way, we take the 2, multiply it times the x, take the 2, multiply it by the 2. That's 2 times 3x. Oops. Plus 2 times 2. We can simplify that. 2 times 3x is going to be 6x. Plus 2 times 2 is
4.
All right. Is it here?
On the 6x plus 4, why can't we put like on 1 behind the x? And, because I'm going to give us the exact same answer.
All right. Now, factoring. So we've had lots of ideas about factoring. You've done factoring a lot. So you've had factoring where you've had a fraction like 4 over 5 times 15 over 8. And you factored. You said, all right, I'm taking out 5 times 3. And I'm taking this out. Oops. I'll leave that as a 4. I'm taking out 4 times 2. And you're doing it so you can cancel. So factoring binomials or polynomials, these are things with more than one term, is going to be quite the same. So factoring is actually the opposite of using distributive property. Because more generally, factoring is undoing multiplications. Undoing multiplications. To take them out. So generally we talk about factoring as a very general term for undoing multiplications so we can take them out in some way or some form. When we're doing it, it's fractions. When we're factoring with fractions, it's so we can cross cancel. If we're factoring with binomials, it's so we can take that multiplication out. And we're going to see what that looks like here in a second. So we're going to start with this. This is just the very basics of how we use distributive properties. So what I'm going to see on your paper is when you are in factored form and you want to use distributive property, you'll just show me that you are multiplying what's outside the parentheses times everything that's inside the parentheses. So this would be the same thing as 9 times 3 plus 9 times 2. And then if I was going to simplify that, I'm going to do all the multiplications that I can here. In this case, I can do it all. 9 times 3 is 27, plus 9 times 2 is 18. These are what we call binomials. And today, except for in your stretch work, we're going to deal with all binomials today. What it means to be a binomial. Let's think about what that could possibly mean. Let's think about the prefix bi. What does the prefix bi mean? Henry? 2. Nomials. Basically means, in this particular case, terms. So this has 2 terms. 1, 2. That makes it a binomial. All right? Let's look at this next one. All right, I'm looking at this, and in order to use distributive property appropriately, actually it just really saves us a step, is we're going to want to have everything be addition. The reason why that's going to save us a step is because if I multiply negative 7 times 5, I'm going to get a negative number, and I'm going to have minus a negative, which means I'm just going to have to leave chain switch at the end. So for me, I think it's always easiest just to have everything as addition. So I'm going to start with a leaf chain switch. And then I'm going to distribute. I'm going to take this negative 7 and multiply it times the a. Take the negative 7, multiply it times the negative 5. So that's negative 7. Negative 7 times a plus negative 7 times negative 5. Now I'm going to do all the multiplication I can. Negative 7 times a, what would we write that as? Jalen?
Or negative 7 times 8.
Yeah.
Or negative 7, 8.
Yeah, negative 7a plus negative 7 times negative 5. Be careful. Be careful. Positive or negative? Positive. Right on. Good date. So the next one, same deal. We're multiplying what's on the outside times everything that's on the inside times each term. I have 3 times 2x plus 3 times 5. Jalen? Yeah. 6x plus 15. Distributive property. Super easy. All right? This next one's going to get a little bit complicated. I'm going to complicate things on you. I'm going to mix things up a little bit here. I have 2x that I am distributing it into both of these parts. So this is going to be, leave yourself a little bit of space here at the bottom. 2x times 3x. I'm doing this at the top of the square because we're going to think about this one in a second. And 2x times 2. So that second part, I think, is going to be no problem. 2x times 2. What's 2x times 2? Axel?
4x.
4x. Nothing unusual there. Now, 2x times 3x. Rashida, what do you think? Definitely have the 6 involved here. Let's start thinking about commutative property here with multiplication. Really thinking about this as 2 times x times 3 times x. I'm going to just commute my terms around. I'm going to have 2 times 3 times x times x. All I did was take all 4 of these multiplications and commute them around. 2 times 3 is x times x can be rewritten as x squared. Okay? Just mixing it up on you. I think you're capable of that. I have friends who teach the same class, one at Bayview, one at Summit. I don't think the way they would try this with their kids. I think the exponents would be too much for them, or I think they think that. But I think that you guys can handle it. All right? So that's why we're doing it today. So when we have those 2 x's being multiplied, remember that's going to give us x squared. All right? We got it? I think we got it. All right. Moving on to the next one. Now the next one's a little bit different. The next one, we're kind of given that form that's kind of in the middle. Now the simplified form is going to be really easy here, I think. Because this tells us 3 times t. 3 times t is what?
3t.
3t. And plus 3 times 5 is 15. That was easy. Now we got to go back the other way. This is that idea of factoring. All right, what is it that I took out? What is it that I multiplied together to get this? Axel, what do you think?
Well, inside of parentheses, that's t plus 5.
All right, so Axel says inside the parentheses is t plus 5. Where'd that come from?
The 3 multiplying t and 3 multiplying 5.
Yeah, so he knows that what he took out here, what he multiplied into both parts was that 3. And so after we take out those multiplications, that leaves us with the t plus 5. Let's go ahead and just prove to ourselves by showing this in reverse really quickly that this is indeed what it is. So I would multiply the 3 times t. That gives me the 3t. And I multiply the 3 times 5. That gives me the 3 times 5. All right, good. This makes sense. This worked. Everybody catch that? Everybody see what we did there? All right. Let's try the next one. Just do the easy part first. The distributive part of this. This is negative 5 times x, which is negative 5x, plus negative 5 times 5 is negative 25. If we wanted to, we could switch that back to a subtraction. I'm going to leave it like this for today, just because I don't want to complicate things any further. All right, here's the tough one. I want to go back to that distributive form, to that factored form. What is it that I factored out here? What multiplication did I factor out? What's the thing being multiplied on the outside here? What got multiplied to both parts? Isaiah. The negative 5. So the negative 5 is what's going to be distributed in. And what did that get distributed into? If I take out those negative 5s, those multiplications of negative 5, what's left? If I take out those multiplications of negative 5, what's left? This is where you've got to be using your brain. If you're not using your brain today, this is where you're going to get hurt in the learning process. Omar, what's going to be left?
X plus 5.
X plus positive 5. Because after I get rid of... We can just kind of think about it this way. After I get rid of those multiplications of negative 5, that's what's left. All right? All right. Next one. The simplified form. That's the easy part. 4 times 3x gives me 12x. And the 4 times 2 gives me 8. All right? All right. What was the part that was factored? What's outside my parentheses? What's going to get distributed in this problem? Aaliyah? 4. And what did that get distributed to? This one you got to be a little bit more careful. It's not tricky, but you do got to make sure your brain's engaged here. What got distributed to? Jalen?
X plus 2. X plus 2, yeah.
So I got to have this 3 in this multiplication over here. So where do I need to put that? I can't put it on the outside because it wasn't distributed to both of them. But I can put it where? If I can't put it on the outside, then I probably have to put it on the inside. It's going to go with the x on the inside. So again, if we want to think about that, like one way we can think about that is if we have it in this form and we just get rid of that thing that we factored out, that's going to tell us what's left, the 3x plus 2. Everybody see that? Kip yes or Kip no? I get this, Mr. Boots. You can give me a... Okay, that's cool. All right, next one. I have this one's tricky going both ways because it's got that thing in there that maybe some of the other schools around here don't think they can handle. I have 7d times d. 7d times d. How am I going to write that? Is it here?
Okay, you put, wait, are you talking about the factored form?
Nope, I want the distributive form. 7d times d. How am I going to write that?
7d squared?
7d squared. Not even a problem. And the 7d times 5 plus 35. Got it. No problem, Mr. Boots. This is too easy. All right. Crystal, question. Oh, yeah, 35D. Sorry. Good catch. I love how she's thinking on her feet. She's thinking about what's going on, and she's catching mistakes. I'm going to give her some guidance for that. All right. Let's look at the factored form. All right, we're over here on the factored form. What got multiplied into both things? What got factored out, Aaliyah? 7D. Okay, we have the 7D is multiplied by both things. What did it get multiplied to? What did it get multiplied to? Isabel. D plus 5, because we can see it when we mark that out. That's what's left. All right, now here comes the really hard one. But we can do this. This is just like factoring with those fractions that we did a long time ago. So I'm looking over here at 12 plus 5. I'm trying to figure out what is my common factor. What is it that I can take out of both 12 and 15? What is it that I can take out of both 12 and 15? Mr. Hayden. 3. So I know that 3 was multiplied times what to give me 12? I know 3 was multiplied by what to give me 12? Jesselyn. 4. And I know 3 was multiplied by what to give me 15? Mr. Hayden. Now we can write it in distributed form. What got multiplied to both things? Rashida?
3.
What did the 3 get multiplied to? Danilo?
4 plus 5.
4 plus 5. Again, if we want to see where that 4 plus 5 comes from, it's like we got rid of those things that we multiplied by. No. Okay, hold on. Give me a second. Sorry about that. Go. And we're back. All right. 5x plus 15. Now we're getting even more complicated. We got those variables in there. What is it that I can take out of both 5x and 15? What is it that I can take out of both 5x and 15? Engage your brains, engage your brains, engage your brains. Zahir.
5.
Okay. 5 times what gives me 5x?
1.
Careful.
Oh.
X. 5 times x. And 5 times what gave me 15? Jesslyn. So, what does my factored form look like? What is it that got multiplied by both things, Andrea?
5
Times what?
3 plus x.
X plus 3 or 3 plus x doesn't actually really matter. So, because of commutative property. All right. Let's keep it going. Let's move the next one. 12x plus 15. What can I factor out of both of those parts? What is it that I can pull out of both of those sets of multiplications? Jesslyn. 3. 3 times something plus 3 times something. All right. 3 times what gives me 12x? Isaiah? 4x. 3 times what gives me 15, Jalen?
5.
And so what is my distributed form?
3 and then 4x plus 5.
3 times 4x plus 5. I don't think you guys realize how amazing you are today. All right, but here's the really hard one. Here's the really hard one. But I think you can do it. Shh. All right. I have 24x squared and plus 16x. What can I factor out of both of these? Omar, what do you think?
2x.
2x, he says. I think we can actually take even a little bit more out of that. 4x, he says. All right. He says 4x because he sees there's an x that we can take out here and there's an x that we can take out here because there's 2 here and 1 here. I think this is the difficult part. 4x times what? Jesselyn? But if we want the x squared, what also has to go with that 6? 6x. Oh my God. They say it can't be done, but it can. All right. 4x times what gives me 16x?
Oh, 4.
4. So my factored form, or excuse me, yeah, my factored form is what?
6x.
SF Base says, no problem. We got this. Yes, sir. Ooh. All right. So this is actually really interesting because now I'm looking at this and Jefferson's saying, hey, this isn't totally factored here. I see now that I'm looking at my simplified form, there's still something that I could have taken out. What else could I have taken out? I can take out an additional times 2, which means that would have made this 8 times 3x and 8 times 2, which would give me 3x plus 2 8x times 3x plus 2. Jefferson getting some guys. Danilo.
It says if you know third to last problem.
Yep.
It says 5x. Could you also put 1x? So like if you don't understand.
Yeah, so if you have to think about this as 1x when you're going through the work, that's totally fine. Just make sure that when you get to that end product, you go ahead and take that 1 off because we don't need it there. So here.
Is it okay if I put like 2x and in parentheses 12x plus 2x and then in 8?
Yeah, so Zahir is saying, hey, what if I had 2 times 12x plus, well, what did it end up being?
2x
Plus 8.
12x.
Or yeah, it would have been 2x times 12x plus 8. So this is not quite factored everything through, and this is where we got to look at our end product and make sure there's no other factors we could have taken out. Okay? So that's kind of that quick check at the end. You guys are amazing. I think you're going to